All right, so this is joint work with James Freitag and Rahim Moosa that I'm going to present today. And so it's going to be about algebraic ODEs and model theory. And so my point of view on this is going to be very model theoretic. But okay, hopefully I'll introduce everything that I need and it should be okay. All right, so the plan is I'm going to ask a question about differential equations. First in vague terms, and then I'll make it more precise, and then I'll translate it into model theory, and then I'll use model theory to solve it. Okay, so that's the plan. All right, so here's my vague question, right? So let's take a field, and let's look at two distinct algebraic differential equations, right? So I'm just taking this irreducible polynomial p and q, and then I'm saying that p of y prime up to y, nth derivative is 0, and same thing with q. Okay, so I'm looking at solutions of these algebraic differential equations. And here's the question. So is there some differential algebraic relation between typical tuples of solution of p and typical tuple of solutions of q? And more importantly, I want to find a solution between these like tuples of solution, and they could be very large. So can I bound the number of tuples that I need to look at to find if there is a relation, right? So, do I need like 100 tuples to find a relation, like 1,000? Who knows, right? So this is the question that I want to answer today. All right. So this is a bit vague for now. And before I make this more precise, I just want to introduce my setup, which is sort of like the first maybe model theoretic step in this talk. So what I'll do is I'll work in a differential field that I'll call U, right? And so that's just a field with a derivation that satisfies Leibniz rule, right? So additive and Leibniz rule, which is differentially closed and saturated. And I'm not going to say exactly what this means, but I'll give you what it entails, right, for us. So what that means for that field is that if I give you a smaller differential subfield, right, so of smaller size, say it's countable and my field U is uncountable, for example, and I give you a system S of differential equations and inequations with parameters in that smaller field F. Okay, so first thing, if it has a solution in a differential field extension of F, then it already has a solution in U. Okay, so I can find solution of whatever I want in that field. Okay, and second thing, which again is sort of important when you're doing Galois theory from a model theoretic point of view, which is what I will do, is that if I give you two tuples of points in that field and they satisfy exactly the same equation and equation over F, then there's a differential field automorphism that fixes F and that moves A to B. Okay, so we can find solution and we can move solutions around in this very homogeneous way. Okay, so this is what this means, right? So you don't need to know exactly what the words mean in model theory or anything like that, but concretely, this is the sort of field that I work with. Okay, so just a little bit more. So all my parameters, all solutions, all fields, everything that I do will live in that big differential field U. Okay, so this is the usual model theoretic point of view on these things, is just take a big differential field. Okay, and this curly C here will denote this field of constants, which is just the field of elements with derivative 0. Okay, so now we all live in here, right? This is where we are. All right, so now I want to define a little bit more what I was talking about on the first slide. So I have to talk about independence and genericity. So let's look at two differential fields, F and K, again in my big field. Okay, so just a bit of notation. This F bracket A is the differential field generated by A over F. So if I have a tuple A, I say it's independent from K over F if, when I take the successive derivatives of A, if I look at their transcendence degree over F and their transcendence degree over K, it doesn't change. Okay, and so right, and this is kind of what I mean by no differential algebraic relation, right? Is that there's no more relation, no non-trivial relation that appear when I move to K, right? Nothing new happens. Okay, then, okay, second definition, if I have tuples A1 through AN, that I say that they are independent over F, if each AI is independent from the field, differential field generated by all of the other ones over F. Right, so it's a lot stronger than just pairwise, right? It's independent of all the other ones. Okay, and of course for the model theorist, this is just forking, right? Right? This is what we call this. Okay, and one more definition. Well, this is unfortunate. Okay, much better. So, again, if I have an equation of the type I considered before, right? So P of y, y prime up to yn equals 0. A solution of it is Cauchy generic, and I'll just say generic in the rest of the talk if it satisfies no simpler equation. And by that I mean either of lower order or maybe of the same order, but of lower degree in this highest order variable. Okay? So it's like, yeah, generic solution, right? Typical solution satisfies no other non-trivial equation. Okay. All right, so with all of this, I can make more precise what I was asking at the start. All right, so, sorry. Yep.
The new equation you for it is over the field, which field?
F, sorry, thank you, same field. Yeah, of course. Yeah, the same field. Yeah. Okay, so here's the precise question, right? So again, I take my two differential equation of that form, assuming again that these polynomials are irreducible. And okay, so here's a condition that, okay, we call CKL in the paper. So if I give you any k independent generic solution A1 through AK of P and L independent generic solution B1 through BL of Q, then these two tuples A1 through AK and B1 through BL are independent over my base field F. Okay, so I give you this number of generic independent solution, this other number of generic independent solution, and they don't talk to each other. Right? There's no new relation over the field F. Right, and so here's the theorem now stated in that form. Right, and so the theorem is that Cn plus 3 and Cm plus 3 implies CKL for all KL in M, right? So if I give you these two equations and I ask you, tell me if there's a relation between these generic tuples of solution, once you found that there's no relation between N plus 3 and M plus 3 of them, you're done. You don't have to go further. Okay? So that's the theorem. So on the next slide, I'll just give some very, very basic examples, right? Nothing really, really basic, but just to show how this sort of works in practice. Okay, so really basic examples, as I said. So consider y prime equals y prime equals 1. Okay, so I mean C11 is true, right? Because if I give you e to the t and t, they're algebraically independent. But of course, C22 is false, right? Because if I take any constant c, then the transcendence degree of these two pairs of solution, right, two pairs of generic solution is less than 3, right? So the transcendence degree drops here. But we need two solutions to see it. It doesn't work with just one, right? So there's really like, you know, just to show that it's really an interesting thing, right? It's not always just one. Okay, and the next example, right, which comes from Oldwork-Rosenlicht, for example, is just an example where you have CKL for all L and K, right? So if I look at, again, y prime equals y, and y prime equals y squared times y minus 1, then no matter how many solutions you look at, if they're independent, you're never going to find any relation. Okay, so you can go forever. Okay. All right, so that's the question sort of formulated in differential algebra. What I want to do now is transform it into a model theoretical question. Okay, and so there's two reasons for that. The first one is that it's the language that I'm comfortable with, so I'm going to use it. The second one is because it actually makes it more general, and the theorem that I'm going to prove is sort of a more general model theoretic theorem that gives you information on other things, right? Not just differential equations. Okay, so types. All right, so again, we're in our big differential field U. and we have a tuple A and some subfield F, the type of A over F is just the set of all differential equations and inequations with parameters in F that are satisfied by A. Okay, and we write type of A over F. Okay, so that's what it is. It's like everything that F has to say about A. Okay, pretty. Right? All the equations, all the inequations, it's all in there. Okay, and if I look at the set of all types over F, we have a notation for this. We call it S of F, right? And types, letters for types, usually is like P, Q, R, S. And then if B bar satisfies all the inequations and equations in a type, we say it's a realization of P. The set of realization, we call it P of U. Okay, is everyone okay with types so far? Okay. All right, so now remember, right, I was talking not just about one solution of my equation, but about tuples of generic solution, right, an independent generic solution, and so this is the type version of this, right? So if I have F algebraically closed differential field and a type P over F, tuples of n independent realization of P, they all have the same type, and I denote it like this, P to the power of parenthesis n, okay, and it's called the Morley power of P. Okay, so again, that's the model theoretic version of independent generic solution of something is this P to the power of parenthesis n, right? Okay, so now, okay, now I'm going, and I have to talk about generic types. So for the rest of the talk, I'll always work over something F algebraically closed, okay? So algebraically closed differential field. And again, pick an equation of that form, right? P of y prime, yn equals 0. And recall that a solution, I call it generic, if it satisfies no differential equation of lower order, of lower degree in y to the n over f, right, over f. Okay, and so the thing here is that all these generic solutions, they have the same type, right? So they're really just all exactly the same equations and inequations, so let's call that type P. And if I look at tuple of n independent generic solutions, they also have all the same type, and it's the type P to the n of the previous slides. Okay? So I did want to write something on the board here. Ah, here it is. So I write very few things on the board, so hopefully it's not too bad. So just, I just want to write this on the board so everyone remembers, right? So types P, Q, R, S, etc. Right? This just means really generic solutions, okay, of differential equations. Right, so really working with types, this is just working with generic solutions instead of just solutions. This is really sort of what I'm doing, right? So it's not, it's just the language is model theoretic, but this is what it means. Okay, so let's see if we can reformulate the question, but for types. Okay, so again, these are just generic solutions of differential equations. We say that these types P and Q are weakly orthogonal if any realization of P is independent from any realization of Q over F. Okay, so they don't have any relation between just like one realization. And we say that they are orthogonal if now I take these like powers of my types, right? So I take n and m independent realization, and they still don't have any relation, right? They are still independent over F. And no matter how many I take, I don't find a relation ever. Okay? So weakly orthogonal, orthogonal, right? And so of course you could say that, okay, orthogonal implies weakly orthogonal, but the converse is false, right? And I gave you an example a bit earlier. And so here's the question for types now. Okay, so let P and Q be types over F. Are there n and m in n such that if I know that P to the n and Q to the m are weakly orthogonal, then I know that they are orthogonal, right? So if I find that after n and m realization there's still no relation, I can conclude that there's no relation ever, no matter how far I go. Okay? So that's the question for types. Okay, so right now that I gave you the question, I'll reformulate the theorem for you using this language, but I need a few more definitions first. Okay, yeah, I have back to the same examples, right, but with the types, and it's really the same examples, right? So if I have P generic of y prime equals 1, Q generic of y prime equals y, and then if these two are weakly orthogonal, but they're not orthogonal because when you take two generic realization independent, you find a relation, okay? So, well, this is really just the same examples, and again, if I have the generic of this equation, y prime equals y squared times y minus 1, this one is orthogonal to the previous ones, okay? So no matter how far you go, there's never any relation. Okay, so this is really the previous examples rephrased in that language of types. Okay. All right, so now I need to define a rank. All right, so let's look at the type over F. The U rank of P is the maximal number of field extension of F that I can take, right? So Fi, F0 up to Fn, such that there is a realization A of P, such that A is not independent at each step of Fy plus 1 over Fi. Okay, so at each step I add some relation. Okay, and the U rank is the maximal number of time I can do that, right? The maximal number of time that I can add a differential algebraic relation. Okay, so we call that the U rank. Okay, so just to remark here, if P is the generic type of one of these equations that I was looking at, we know that the U rank is smaller than N, but it's not an equality in general, and Ronnie in the next talk will give many examples of this, I assume, right? So, right, so I'm not going to give any, but you'll see a lot later, right? But it's an inequality, it's not an equality. Okay, and so here's the theorem rephrased in this language of rank. So if I have two types P and Q over F, if P to the U of P plus 3 is weakly orthogonal to Q to the U of Q plus 3, then they are orthogonal, okay? So if I know that there's no relation between this many tuples of realization independent and this many tuple of realization independent, then I know that there's never any, okay? Right, and of course, because this is not an equality in general, this UP less or equal to N, that means that this is slightly stronger than what I said at first, right? It's a little bit stronger. Okay, so one more definition. And after that, I think I'm almost done with definitions. So, okay, so I say a type P is minimal if it has U rank 1. Okay, so smallest possible U rank without being 0. And okay, if you unpack a little bit what this means, it means that if I give you any realization A of P and the field extensions that A is not independent of K over F, then it must actually be algebraic over K. Okay, so anytime I add some differential algebraic relation, it's because I become algebraic. Okay, and so the key tool here, which sort of allows us to do this, and this is really a general model theoretic fact. It's nothing about DCF, really. It's nothing about differential equations. If I have two types P and Q over the same set of parameters F, and they are not orthogonal, then there is a minimal type over F such that they are both non-orthogonal to this minimal type, right? So you have some sort of factorization, right? If I know P and Q have some sort of relation, I can find this minimal type R and factor through this minimal type, okay? And again, this has nothing to do with differential equations. It's a general model theoretical fact, right? Okay, and the observation here also is that, and you know, this is something you can just prove, is that if P to the K is not weakly orthogonal to that minimal type, and Q to the L is not weakly orthogonal to that minimal type, then P to the K is not weakly orthogonal to Q to the L. Okay, so this is sort of like the first reduction for the proof, right? And the proof is going to be sort of by successive reduction to like more and more specific things. And so this is the first one. Right, so the question now is reduces to pick some p and some r, and r is minimal. Find the smallest natural number such that if p is non-orthogonal to r, then p to the n is not weakly orthogonal to r. Okay, so we started with two arbitrary types, p and q, and now actually we reduce to having one of them being minimal. Okay, so this is the first reduction. Okay, great. And okay, why is this very nice to reduce to minimal types? I'll tell you. This is because of, I think, yeah, one of the main results of, like one of the greatest results of model theoretic differential algebra is the Hilbert's dichotomy. So, okay, if I have a minimal type over F, it must satisfy one of the following mutually exclusive possibilities. Either it's locally modular, and I'm not going to define this, but you can think of it as inside of R, there's not much happening. Okay, the geometry inside of the realization of that type, okay, nothing complicated is going on. Okay, and otherwise, if it's complicated enough, it's non-orthogonal to the generic type S of the field of constancy. Right, and by the generic type S of the constancy, I mean the type of some element that's in the constant but not in F. Right, and F is algebraically closed. Right, so there's really one thing here. Okay, so that's the Hilbert's dichotomy. So how does that affect what we want to do? Well, basically, if R is locally modular, you get a bound of 2. Okay, so you don't have to worry about it. And this is again a general model theoretical fact. I may say a little bit more about how one could get this later, but for now, you can trust me, right? That if R is locally modular, you just get 2. Okay, now. If R is non-orthogonal to the generic type of the constants, again, this is an easy exercise to show that it means that P itself is non-orthogonal to the constants, to the generic of the constants. Okay, so again, we're like now reduced to something even more concrete, right? We have R type P, and we're trying to, and we say, okay, it's not orthogonal to this generic type of the constants, and we want to find a bound for not weak orthogonality. Okay? Okay. All right, so this is what we've reduced to now, right? Let P be some type over F, and assume that P is not orthogonal to this generic constant, right? So we know that some long tuple of independent realization of P has some relation with some constant somewhere. What is the smallest such tuple? Okay. Okay, and okay. One last reduction. All right, so we will further reduce to types that are called C internal. So if I have a type P over F, I say it's C internal if I can find a field extension L such that all realization of my type are in the differential field generated by the constants and L. Okay, and so on the next slide I'll talk a bit more about this, but an example is linear differential equations. Okay, solution of linear differential equations are C internal, but it's not like they are not the only C internal types. Okay, so again, general model theoretical fact here. If P is non-orthogonal to R, then for any realization of P, A, there is some B in the differential field generated by A and F, such that the type of B is C internal. Okay, so now I'm reducing to C internal type, right? Because, of course, because B is in that field, if I can find some relation with that B, I can find it with A too, right? Because B is just some polynomial, some differential polynomial in A, right? Okay, so now we also can assume that P is C internal. All right, so, okay, and so why is it nice? Is because we can do differential Galois theory, right? So here's the model theoretical version of the differential Galois group. So let's have a C internal type over F. And what I do is I consider this group out of P over C. And so what this is for me is I restrict the automorphism of my big differential field U to the realization of P, right? And by automorphism, I mean differential field automorphism, right? So it respects the algebraic operation and the derivative. Okay, so the key point here is this group is isomorphic to a definable group acting definably on P of U. And okay, we also call that group ODE F of P over C. And moreover, this group is definably isomorphic to the constant points of an algebraic group. Okay, so I don't want to say, right, the word in blue definable. I just want to say a bit more about what this is. Again, I don't want to define it too precisely. But okay, so there's a few ways to do this. Definable could mean just union, intersection of differential equations and inequations. Okay, so that's one way to say it. Right? So definable. Okay. Unions, intersections of solution of differential equations and inequations. Okay, so this is one way to see it. Or you could say, you know, you have a topology called the Kolchin topology, which is like the Zariski topology for differential algebra, and this also just means constructible in that topology. Okay, so essentially it's anything you can make out of differential equations and inequation, and you union them, you intersect them, and then you can talk about definable function, if their graphs are definable, etc., etc. Okay? So again, I'm being a bit vague here, but I hope everyone gets roughly what's going on, right? So okay, so here's an example, right? And I said that on the previous slide. So if I have a linear differential equation, y prime equals a times y, the generic type of this is C internal, and in fact, this group G is the Galois group H of Remy's lecture, or at least it's isomorphic, right? So this is really the same object that we're talking about here. This is a bit more general because it could apply to nonlinear differential equations, but for linear, it's the same thing. Okay. All right, and so whenever I have a C internal type, I get an algebraic group action. Okay, so that's the moral of the story. Okay, and so here's where you have to like study a little bit algebraic groups to make this work. So if I have a connected algebraic group action GS, I say it's generically transitive if there is an orbit O such that the dimension of S minus O is strictly smaller than the dimension of S. So it has a very large orbit, right? Maximal rank orbit. Okay, and I say it's generically n-transitive if now I look at the action of G on S to the n, coordinate-wise, this is generically transitive. So not only it has a big orbit in S, it has a big orbit in S to the n. Okay, so first fact is that if the action is not transitive, then we get not weakly orthogonal even. Sorry, this should be a weakly here, right? So we get a relation between one solution and one constant, right? So this should be weak here. Okay, so we can assume safely that the action is transitive, and then here's a lemma, is that if this action is transitive, then it's definably isomorphic to an algebraic group action, GS. Okay, and moreover, if P to the n is weakly orthogonal to the generic of the constants R, then this is generically n-transitive. Okay, so now we're actually almost done, right? So all we need to do now, right, if we want to bound this, is to bound generic n-transitivity. Okay, we want to bound the degree of generic transitivity of our group actions, and so this is a result, right? This is something we know how to do now. Right, and so now we're done, right? So this is a theorem of Freitag and Moosa after work of Popov, which is that if I give you an algebraic group action GS where S is of dimension n, then it is at most generically n plus 2 transitive. Okay, you can't go higher than this. And in that case, okay, even more, I'm not going to use it here, but in that case, it's isomorphic to PGLN plus 1 acting on Pn. Okay, so there is really a bound here. And we get the result straight away, right? After all of these reductions, we get the result. Right, so the corollary is that if P is C internal, then P to the U of P plus 3 is not weakly orthogonal to the generic type of the constant. Okay, and from that you get the theorem, right? Now we did all these reductions to this situation exactly, and so now I know that if I have any type P of Q over F, if P and Q are non-orthogonal, then these powers of them are not weakly orthogonal. Okay, so that's the sketch of the proof of that result. Is there any question about this? Okay. How many time do I have left, by the way? I'm not sure at what time I started. 20 minutes? Okay, that's great. Yeah. Okay, so now I want to show you why this bound is optimal. Okay, so this is the next part of my talk. I showed you that we have this bound. I want to show that it's the best possible. And there's no reason why it should be the best possible, right? Because at this step here, we said there's a relation between P and Q, and we factored it through this thing, right? But maybe we could do better if we didn't do that, right? So a priori, there's no reason why this is the best possible, but it is. Okay, so, all right, so sometimes we can do better by doing this. Okay, so if F is an algebraically closed field of constants, and I have a C internal type, with binding group acting transitively, if this Galois group is linear, then it's actually abelian, and in particular, because it's abelian, you get P squared not weakly orthogonal, again, to R, right? And so then, this is a result of Galois-Moosa that if F is an algebraically closed field of constants, and PQ are types over F, if they're non-orthogonal, then P squared and Q squared are already not weakly orthogonal. Okay, so if we're working over constant parameters, we just get a bound of 2. Okay? So in that case, you get much better. And okay, and by the way, I just want to mention this very quickly, but you could also recover, remember, I said something about this R being like locally modular and you get a bound of 2. It's for the same reason, okay? It's because you can do Galois theory in model theory over any type, and if R is locally modular, any group definable in there is abelian by finite, okay? And so you get the same result for that reason. Okay, so if you're over a field of constants, you get much, much better, right? You get just this bound. But okay, so in general, the bound is optimal. So what do I mean by that? So if I give you any n and m natural numbers greater than 0, I can find a differential field F algebraically closed and P and Q over F such that the U rank of P is n, the U rank of Q is m. They are not orthogonal, but they have the highest possible powers that are weakly orthogonal, okay? So, right, what that means is that I can take UP plus 3 realizations of Q, of P and UQ plus 3 realization of Q and find some relation between them. But if I have one less, I can't do it, right? This is what this means. So. Okay, so what's the idea here? I mean, of course, we know that we get the greatest possible bound, right? Our theorem got the bound by looking at actions of, PGLN plus 1 on Pn. So this is the idea, right? We want to start with types that have this action of, say, PGL U of P plus 1 acting on P U of C. And so this is a lemma, right? Freitag and Moosa did this. Maybe this was known by other people. I'm not sure, but okay. Such types exist over field F, which are generated by independent differentially transcendental elements. And that will be important in the proof later, okay? So if I give you some field generated by these differentially transcendental elements, I can find types with Galois groups PGL n+1 acting on Pn, where n is the rank of my type. Okay, so that's the first step, is to find these types, but that was done already. Okay, now, all right, so if I give you two types over the same set of parameters f, I can do a slight modification of the Galois group, which is now I restrict, again, my automorphism of u to the type P, but instead of asking that it fixes f and the constant pointwise, I ask that it fixes f, the constant, and the other type. Okay, so it fixes more things. Okay. And so, of course, you know, again, this is sort of general model theory, but this is a normal subgroup, and it's definable as well, right? And it acts definably on P. Okay, and so again, another lemma is that if I quotient, right, so if I quotient odd of P by odd of P over Q, and then odd of Q by odd of Q over P, these are definably isomorphic. So if I remove the word definably here, this is just Gorsat's lemma. So the proof is really to prove definably, right? And this is something Christine Ingalls and I have used, but I think maybe it was known also by other people. So, yeah. Okay. So this is really just, this is the idea, okay, is to use this. Okay. So again, let R be the generic type of the constants, and okay, we have this lemma, which is really just a nice Galois theory exercise. So if I know that P to the n is weakly orthogonal to R, and Q to the m is weakly orthogonal to R, and I know that when I look at these binding groups of P over Q and Q over P, that is the same. Okay, so it doesn't change. Then I can conclude that these types are weakly orthogonal. Okay, so somehow that means that when I did this factorization here, it didn't change anything, right? And it's really just like a Galois theory exercise to do this. Okay, and of course, if these groups, right, are non-isomorphic simple group, then this is always true, right? So, okay, I mean, so somehow we win in this case, right? So. Right, so if P and Q over F are C internal type with binding groups PGL UP plus 1 acting on P of PUP, right? And same thing for Q with different ranks, then we get this already for free, just from this lemma and the fact that these groups are simple, not isomorphic. Okay? Okay, so I mean, of course, this, you know, what if U of P equals U of Q, right? This is actually the hard case because now we can't exclude that, right? We can't exclude that the group, right, out of P over CQ, maybe it's the identity now. Okay, this is possible now, right? If the two groups are isomorphic. Okay, so the way to do this, right, if they have the same rank, is to consider a family of types. Okay, so now I'll give a bit more details. So really what we have is we have a differentially transcendental tuple, let's call it B bar, and some F B bar, which is just the algebraic closure of the differential field generated by B bar. And then we have this type P sub B bar with binding group PGLN plus 1 acting on Pn. Okay, where n is the U rank of my type. And of course, I can vary this B bar, and I have this whole family of types, right? And so now what we want to do is to find some B1 bar and B2 bar, such that, again, we have the same two equalities, right? Because we know that once we have this, we're done, right, by the previous lemma. Okay. Right, so we just have to do this now. And then, okay, the proof now is by contradiction. Okay, so let's assume that this is not the case, right? So if this is not the case, then this is what we get, right? By simplicity of this binding group, of this Galois group, we get that out of PB1 over C and PB2 is just the identity. Okay, so really what that means, and this is a bit more model theoretical terminology here, but let me explain it. This implies that this family is uniformly internal to C. Okay, and what that means is I can find an extension of Q-alg that I call K, such that for any B bar and any A in that fiber, right, in that PB bar, A is in the differential field generated by the constants, K and B bar. Okay, and so really the point here is that K does not depend on B bar, right? Because we know, I mean, I know all these fibers are internal, so I know I can find such an extension for any fiber, fiber by fiber, but here I can do them all at once with just one field. Okay, so this is the key point here. Okay, and why is this nice? Okay, so we have the following proposition by Jaoui, myself, and Pillay. This actually implies, because the type of B bar, this should be the type of B bar here, not PB bar, just B bar, right, the type of the base. Because this is orthogonal to the constants, actually this means that this family PB bar, it's very simple. It's in generically finite to finite correspondence with the type of B bar over Q-alg and some type P that's C internal and over Q-alg as well. Okay, so it's just a product of the type of the base and some type over Q-alg. Just a product. Okay, and then, okay, you can do a little bit of arguments here. This implies that the binding group, Galois group of that type P over C and the Galois group of any fiber, they are isogenous. Okay, but that's impossible, right? That's the final contradiction because this one, because as I said before, it's over something constant, it's abelian, and this other one, it's PGLN plus 1, right? So they can't be isogenous. So there's no way this happens. Okay, and that concludes the proof, right? So this is the hard case of the proof where the binding groups are the same, but you can get it by this sort of like make the binding group be over the constants, right? And you do that argument. All right, so I'll end my talk with just a few more questions around these methods and ideas. So the first one is, okay, I showed the bound is optimal, right? I showed that the bound is the best possible, but okay, there's one assumption still, right, is that we're asking that we pick independent realization of our equations, right, or of our types. But what if we don't ask that? What happens? Can we get a better bound? And okay, we don't know. But it reduces to the same question, okay? So if P is C internal, we want to find a relation between not necessarily independent realizations of P and some constant in C, okay? And okay, what's encouraging here, and that's kind of what we have so far, is that, right, for the worst possible case, in the independent case, right, which is PGLN plus 1 acting on Pn, we actually have a bound of 4, okay, by doing some geometrical argument, you pick points in a line, stuff like this, right? But the general case seems kind of too difficult at that point, at least to me. Okay, so that's one thing, and it would be nice to have a lower bound here. And then the other one that I would like to think about is generalize this method that I showed before, right, of like having this family of types and having the Galois group be isogenous to something over the constants. It would be nice to have this without the assumption that this type of B bar is orthogonal to the constants, right? That would like maybe allow for more applications. Okay, so that's all I had for today, so thank you.